Okay, let's discuss some few problems in calculus 4, and we'll begin with this problem here. Find the maximum and minimum values of the radius of curvature rho for the graph x is cosine t, y is sine t, z is sine t, for t is between 0 and 2 pi. So we want to calculate the minimum and the maximum values of the radius of curvature of this curve here. So the curve is given by r of t equals cosine ti plus sine tj plus sine tk, for t is between 0 and 2 pi. So the curvature is given by the magnitude of the cross product of the first derivative and the second derivative, divided by the magnitude of the first derivative cubed. So the first derivative is the derivative of this curve here. The derivative of cosine t is negative sine t. The derivative of sine t is cosine t. The derivative of sine t is cosine t. So that's the first derivative. The second derivative is the derivative of the first derivative. The derivative of negative sine t is negative cosine t. The derivative of cosine t is negative sine t. The derivative of cosine t, negative sine t. So the cross product of the first derivative and the second derivative is 0, -1, and 1. So you just compute a cross product and you'll get this. So the magnitude of the cross product is square root of 2. It's going to be 0 squared plus -1 squared plus 1 squared. Square root of that is square root of 2. The magnitude of the first derivative cubed is sine squared t plus 2 cosine squared t raised to 3 over 2. And since sine squared t is 1 minus cosine squared t, replacing sine squared t will give us 1 plus cosine squared t raised to 3 over 2. Now, so rho, which is the radius of curvature, is 1 over k, which is given by these values. We computed this in the previous page. So by inspection, we can see that the maximum radius of curvature occurs when cosine squared t is 1, and the minimum occurs when cosine squared t is 0. But using calculus 1, the derivative of rho is rho prime of t is 3 over square root of 2 times square root of 1 plus cosine squared t, cosine t, sine t. Just use the chain rule to find the derivative of this. Setting this to 0 gives these critical values. T is 0, pi over 2, pi, 3 over 2. Remember, we say that the minimum occurs when cosine squared t is 0, and the maximum occurs when cosine squared t is 1. So if cosine squared t is 0, that means t can either be 0 or it can be pi. Okay. Cosine squared t is 1, not 0. Is 1. So we have rho of 0 equals rho of pi, which is equal to 2. Okay. But for cosine squared t is 0, t can either be, t is pi over 2, okay, or 3 pi over 2. So cosine, rho of pi over 2, you plug in pi over 2 here, will give you 1 over square root of 2. So this is the maximum radius of curvature, and this is the minimum radius of curvature. You can test this using the first derivative test, and you'll see that this is true. Okay, next problem. Evaluate the double integral, this double integral. So we are finding the volume of a region that is sitting on this curve, x squared is really a circle, x squared plus y squared is less than or equal to 0 inside this circle. That's the region R. Okay. So moving on here. So we can convert this into polar coordinates because this is one circle. We have from 0 to 2 pi. That's theta is from 0 to 2 pi, and the radius is 1. So r times, okay, this r here is x squared plus y squared square root, which is r when you convert it to polar coordinates. R dr d theta is dA. When you compute this, you will get that. And we can graph this region so we can see exactly what figure we are finding its volume. So if I stop sharing here and share another page, let me see here. One second. If I can share this. Yes, this is it. Okay, so let me plot that. So it was z equals square root let me just type in square root of x squared plus y squared. Okay, so is this region here? So it's really the volume of a cone with radius 1. Okay, so you can see it here. But it's a little bit complicated when it's in a xy plane. So we have to change it to polar coordinates to make it easier for us to integrate. So that's it right there for this problem here. And let's see, let's go back to the solution. So I'll stop sharing real quick. Okay, now let's share this. Okay, so we have converted into polar coordinates. And when you compute this is just basic computations from calculus 1, and that volume is 2 pi over 3. Okay. Now, next problem. Now, this one, we have to use transformation. U is x minus 2y, v is 2x plus y, to find this double integral here, where the region R is given by this. If you plot these lines in 2D, you will see that it's not a nice region. It's not a rectangle or a triangle. So we have to use the Jacobian to make it more of a rectangle, something that we can simply integrate over it. So I can show you exactly how this function z equals to x minus 2y over 2x plus y. Let's look at the graph of that before we can convert or use Jacobian to transform this figure here. So let's go back to Desmos. So we're gonna share, give me 1 second again. So let's share it. Okay, so I'm going to deactivate that. And this is the region they're talking about. But you can see that it's really ugly. They're not, like, if you look at that, it's not really rectangular form sitting on the XY plane. So we need to change that. Yeah, we need to change it. I'm trying to make you believe that this is not nice. You see, look at that line right there. So it's not really a rectangle. So we need to transform it into a nice region on the XY plane. So we can simply integrate over that region. So when we do that, so I'll go ahead and show you how nice it is after we convert it into using Jacobian. So when we convert it into Jacobian, we will get something nicer like this. So you can see how straight these edges are. Yeah. They are kind of rectangular. So it's better than the original function in XY plane. So we have to transform it into UV plane instead of XY plane using the Jacobian. Okay, so this is nice. So we need to convert this region here into this. Okay, so let's go back to the problem. Okay, here is the problem here. So this is the problem. Now let's look at the solution. So this is the problem here. We want to integrate this over the region R. So x minus 2y equals 1 implies that u1 is 1. X minus 2y is 4 implies that u2 is 4. 2x plus y equals 1 implies that v is 1 or v1 is 1. 2x plus y equals 3 implies that v is 3 or v2 is 3. All right. So now, so the numerator x minus 2y is our u, and 2x plus y is our v. So we have u over v. And we have then we have to compute the Jacobian or the determinant. Not really the determinant. Yes, that's the matrix. So it's the determinant of the Jacobian, the absolute value of the Jacobian. So now when you solve this for u, you get 1 to 3. When you're in U plane, so it's 1 to 3. And then 1 to 4. Okay, we need to recheck that. Okay. So now, so that's in U plane. Okay, so the Jacobian is the determinant of this matrix, dx du, dx dv, dy du, dy dv, which is the same as this when you invert it. Okay, so, and we end up with 1 over 5, because the determinant of this matrix is 5. Okay, 1 times 1 is 1, minus negative 4, you get 5. All right, so that's the Jacobian. Now, we can do the integration now over the nicer region. So we have this. This is really calculus 1. You can simply compute this. That's easy enough. All right, so and the answer is 3 over 2 ln 3. Okay. Next problem, find the local maxima, minima, and saddle points of this function, 3D function. Here, we can graph this so you can see what they are talking about. So I'll stop sharing and go back to the calculator. Okay, let's share that. So this is the function. I'll deactivate that, and we have this. So we need to. So it looks like the Gaussian in 3D in statistics. So the normal graph. So we want to find the volume of this thing. Okay. So how do we do that? Not really the volume. We want to find the relative maxima, relative minima, and the saddle point, if there's any saddle point. But we don't see, from the graph here, we don't see any saddle point, but there is a maximum here. So let's look at that. Okay, so I'll stop sharing again. Then we go back to the problem. Okay, so here's the problem. Now let's look at the solution. We want to find the relative maxima, minima, and saddle point, if there is any. Okay, so the gradient of this function is this. When you take the derivative with respect to x and then the derivative with respect to y, we have this is the gradient. Okay, so setting this to 0, so this gradient is 0 when x is -1 and y is 0. When if you plug